Imagine a single flash of light that has traveled across the universe for billions of years, carrying the memory of a collision that reshaped the cosmos. That faint whisper, stretched beyond the reach of any eye, is the echo of an ancient crash, an event so vast that it set the pattern for galaxies, stars, and even the space between them. In the darkness of the early universe, massive clouds of gas and dark matter began to drift together, pulled by a force that knows no limit. Their slow, inevitable dance forged the scaffolding of the cosmos, a grand web that still holds the universe together today. From the moment the first particles formed, the universe was a restless sea of possibilities. Tiny fluctuations in density, imperceptible ripples in an otherwise uniform expanse, seeded the growth of structures that would later become clusters of galaxies. These fluctuations were not random. They were the imprint of the very first collisions, the first moments when gravity began to dominate over the frantic expansion that followed the birth of space itself. As these regions grew denser, they attracted more matter, and the process accelerated, turning a smooth fog into a complex tapestry of filaments and voids. The scale of this architecture is hard to picture. If the sun were reduced to the size of a marble, the Milky Way would stretch across a football field, its spiral arms reaching out like faint brushstrokes. Yet the entire cosmic web extends far beyond the reach of any single galaxy, spanning hundreds of millions of light years. In that span, the distance between neighboring clusters is comparable to the distance between the sun and the farthest edge of the solar system, multiplied many times over. Each filament is a river of dark matter, invisible yet essential, guiding the luminous galaxies that sparkle along its banks. When two massive structures finally meet, the encounter is not a gentle touch but a cataclysmic merger. The energy released in such a collision dwarfs that of any supernova, shaking the very fabric of space-time. This trembling is recorded as gravitational waves, ripples that travel outward at the speed of light, carrying with them the story of the event. Though the waves are faint by the time they reach us, a background hum of countless ancient collisions fills the universe, a persistent murmur that has survived since the first great mergers. Detecting this gravitational wave background is akin to hearing the distant thunder of a storm that raged before the first continents formed on Earth. These waves are not the only relics left behind. The universe keeps its own archives, preserving clues in the form of cosmic microwave background radiation, ancient star clusters, and the elemental composition of distant gas clouds. Each relic is a time capsule, a snapshot frozen at a particular moment in the universe's long history. When we examine the oldest stars, we find that they contain a higher proportion of hydrogen and helium, the primordial ingredients forged in the first minutes after the Big Bang. Heavier elements, such as carbon and iron, appear only after successive generations of stars lived and died, spreading their ashes across space. The presence of these elements in a distant galaxy tells us that many cycles of birth, collision, and rebirth have already taken place. The notion of time itself stretches under the weight of these events. A single collision between two galaxy clusters can take billions of years to complete, a period that dwarfs the entire span of human civilization. Yet within that immense interval, the universe continues to evolve, forming new structures while erasing old ones. The remnants of a collision may linger as a faint glow of hot gas, a distorted galaxy, or a subtle shift in the motion of surrounding objects. Over eons, these signatures fade, becoming part of the background that future astronomers will have to decipher. Our own planet is a tiny witness to this grand drama. Earth orbits a star that is itself a modest member of a spiral arm, a branch of the Milky Way that has been shaped by countless past mergers. The sun's path through the galaxy is not a straight line but a gentle wobble, guided by the gravitational pull of nearby massive structures. In the deep past, A close encounter with a passing dwarf galaxy may have stirred the outer reaches of the Milky Way, sending streams of stars into new orbits. Such events are invisible to us on a daily basis, yet they are recorded in the motions of the stars we can see. The mystery that surrounds these ancient collisions is both humbling and inspiring. We can map the large-scale structure of the universe with powerful telescopes, tracing the filaments that connect clusters like veins of light. We can listen for the faint whispers of gravitational waves, using detectors that are sensitive enough to feel the tremor of a distant merger. But many questions remain unanswered. What is the exact nature of the dark matter that shapes these structures? How did the earliest collisions influence the distribution of the first galaxies? Could there be hidden forces, beyond our current understanding, that guided the growth of the cosmic web? Each new observation adds a piece to the puzzle, yet the picture never becomes complete. The universe is a living archive, constantly rewriting its own story as we learn to read its language. In the silence between the stars, there is a resonance that speaks of power beyond imagination. A reminder that everything we see, from the smallest grain of sand to the brightest quasar, is part of a larger narrative that began with a series of ancient crashes. As we stand beneath the night sky, the stars above us are not merely points of light. They are beacons that have survived the tumult of countless collisions. Their steady glow is a testament to resilience, a quiet affirmation that even in a universe forged by violence, order can emerge. The echoes of those primordial impacts still travel through space, waiting to be heard, waiting to be understood. In the chapters that follow, we will follow these whispers deeper into the darkness, tracing the pathways of hidden forces and unveiling the secrets that ancient collisions have left behind. The journey will lead us to the heart of the gravitational wave background, to the hidden corridors of dark matter, and to the very edges of time itself. For now, let us pause and feel the weight of the cosmos, a vast, silent symphony composed over billions of years, and recognize that we are listening to a story that began long before our world took shape. The next step is to turn that faint murmur into a clear voice, and to let the universe tell us how it came to be. Imagine standing beneath a night sky so clear that the Milky Way unfurls like a river of light, and yet feeling the pull of a force you cannot see, a hidden hand that shapes the very pattern of the stars. That unseen hand is dark matter, the invisible scaffold upon which the universe builds its grandest structures and stages its most violent collisions. It is the quiet architect whose presence is felt in the way galaxies gather, the way they spin, and the way they smash together across distances that stretch beyond imagination. The story begins with a simple observation. When astronomers point a telescope at a distant galaxy and measure how fast its outer stars orbit, they find that those stars move far faster than the visible matter alone should allow. The luminous disk of stars, gas, and dust accounts for only a fraction of the mass required to hold the galaxy together. The rest must be hidden, an ocean of matter that does not emit, absorb, or reflect light. This invisible component is what we call dark matter, and it gathers in vast, spherical envelopes that surround every galaxy like a ghostly halo. These halos are not uniform clouds. They are massive, extending far beyond the bright edges of their galaxies, and they contain the lion's share of a galaxy's total mass. If you could weigh a typical spiral galaxy, you would find that dark matter contributes roughly 5 times more mass than all the stars, gas, and dust combined. In a sense, the visible galaxy is a tiny lighthouse perched on a colossal, unseen iceberg. The iceberg's bulk determines how the lighthouse stays upright, how it drifts, and how it interacts with neighboring icebergs. When many such icebergs, galaxies, populate a region of space, the dark matter halos begin to overlap and interlock, forming a cosmic web. This web resembles a vast network of filaments and nodes, where filaments are strands of dark matter stretching across hundreds of millions of light years, and nodes are dense knots where the filaments intersect. Galaxies are drawn along these strands, much like beads sliding on invisible strings, gathering at the intersections to form clusters and superclusters. The pattern of galaxy clustering we observe today, clusters, walls, and vast empty voids, mirrors the underlying dark scaffolding. One of the most compelling ways we have learned about this hidden architecture is through gravitational lensing. Einstein taught us that mass bends the path of light, and when a massive object lies between a distant source and an observer, it can act like a glass lens, distorting and magnifying the background light. By carefully measuring these subtle distortions across the sky, astronomers can map where mass resides, even when that mass emits no light. The resulting maps reveal concentrations of dark matter that line up with the luminous galaxies, confirming that the invisible halos are indeed the scaffolding guiding the visible structures. The influence of dark matter extends beyond merely holding galaxies together. It also dictates how they meet and merge. When two galaxies approach one another, their dark matter halos are the first to feel each other's gravity. The halos, each extending far beyond the stellar disks, begin to intertwine long before the bright stars ever touch. This early interaction slows the galaxies, drawing them into a shared orbit and setting the stage for a dramatic merger. As the halos interpenetrate, they create tidal forces that strip away gas and stars, forming spectacular streams that arch across intergalactic space. The visible fireworks of a galactic collision, long tidal tails, bursts of new star formation, and the eventual coalescence into a larger galaxy, are all choreographed by the unseen dance of dark matter. Consider a familiar analogy from everyday life. In a bustling city, the streets and sidewalks guide the flow of traffic, but the true support lies beneath the pavement. A network of steel beams, concrete foundations, and utility tunnels that no passerby sees. Those hidden structures bear the weight of the buildings, channel water, and allow electricity to flow. If the underground framework were to shift, the city above would tremble, roads would buckle, and buildings might collapse. Dark matter plays a comparable role on a cosmic scale. It is the steel framework of the universe, unseen yet essential, shaping the motion of galaxies and the timing of their collisions. The mass of a dark matter halo can be staggering. A typical halo surrounding a galaxy like our own Milky Way contains roughly 1 trillion times the mass of the Sun. To picture that, imagine a sphere whose radius stretches out to about 300,000 light-years, far beyond the bright disk of stars, filled with an invisible substance that outweighs the visible galaxy by a factor of 5. When two such halos approach, their combined gravitational pull is immense, pulling not only stars but also the surrounding intergalactic gas, guiding it toward the collision site. This process fuels the intense bursts of star formation that astronomers observe in merging galaxies, illuminating the night sky with new stellar nurseries that would not exist without the dark scaffolding. Even the most distant and ancient galaxies, seen as they were billions of years ago, already exhibit the imprint of dark matter. In the early universe, fluctuations in the density of dark matter seeded the formation of the first halos. Over time, these halos attracted ordinary matter, allowing the first stars and galaxies to ignite. The pattern of those early structures, captured in the faint glow of the cosmic microwave background, shows the same web-like distribution that we see today. It tells us that the invisible framework has been guiding cosmic evolution since the universe was a fraction of its current age. Yet, despite its central role, dark matter remains a mystery. We know it exists because of its gravitational effects, but we have not yet detected a single particle of it directly. Its composition is unknown, and many theories compete to explain its nature. Some propose that dark matter consists of slow-moving particles that rarely interact with ordinary matter, while others suggest more exotic possibilities such as hidden dimensions or modifications to gravity itself. The unanswered questions linger like shadows behind the scaffolding, reminding us that our understanding of the cosmos is still incomplete. As we contemplate the invisible architecture that shapes the universe, we are drawn to reflect on the nature of what we cannot see. The same way a child learns to trust the solidity of a table by feeling its surface, astronomers learn about dark matter by observing its influence on light and motion. The universe invites us to infer the unseen from the patterns it leaves behind, to read the story written in the bending of starlight and the clustering of galaxies. In each merger, each tidal tale, each burst of new stars, the hidden scaffolding whispers its presence. The next chapter will take us deeper into the aftermath of these colossal collisions, where the remnants of dark matter and the debris of galaxies coalesce into new, massive structures. We will follow the echoes of ancient impacts, tracing how the invisible framework continues to shape the destiny of the cosmos. For now, let us hold the image of the unseen scaffolding, a silent, massive lattice that binds the universe together, and feel the wonder of a universe where the most powerful forces are those we cannot directly perceive. When a star dies, the sky lights up like a cosmic fireworks display, a fleeting brilliance that reshapes the galaxy and whispers the story of ancient collisions. In that brief blaze, the universe reveals a secret language written in light, particles, and expanding shells of gas. It is a language we have learned to read, and through it we glimpse how the violent ends of massive suns sow the seeds for new worlds. The most spectacular endings belong to stars many times heavier than our sun. These giants spend millions of years fusing hydrogen into helium, a process that steadies them against the relentless pull of gravity. When the fuel in their cores finally runs out, the balance tips. The core, now mostly iron, can no longer generate pressure through fusion. Gravity wins, and the heart of the star collapses in a fraction of a second, shrinking to the size of a city while holding the mass of 1,000,000 suns. This sudden implosion triggers a shock wave that races outward, tearing the outer layers apart. The result is a core collapse supernova, a cataclysm that can outshine an entire galaxy for weeks. Not all supernovae begin with a collapsing core. Some arise from a very different drama, a white dwarf, the dense ember left after a sun-like star has shed its outer skin. In a binary system, this ember can steal material from a companion star. As the stolen gas piles onto the white dwarf, its mass grows inch by inch until it reaches a critical limit. At that point, the pressure and temperature become so extreme that carbon and oxygen ignite in a runaway fusion reaction. The star detonates in an instant, leaving no remnant behind. This is a Type Ia supernova, a brilliant explosion that serves as a cosmic yardstick for measuring the expansion of the universe. Both kinds of supernovae leave behind spectacular nebulae, glowing clouds that drift through space like the afterglow of a fireworks burst. In a core collapse event, the inner core may compress into a neutron star, a sphere only a few dozen kilometers across, yet packing more mass than the sun. Around it, the expelled gas expands, forming structures such as the Crab Nebula, where filaments of ionized gas twist and turn under the influence of magnetic fields. In the case of a Type Ia, the blast disperses the white dwarf's material into space, creating a more uniform, spherical shell that slowly fades as it mixes with the surrounding interstellar medium. These nebulae act as markers, tracing the locations where massive stars once lived and died, and pointing to the violent collisions that forged them. The true importance of these explosions lies in the elements they scatter. Inside a massive star, nuclear furnaces forge elements from carbon up to iron, each step adding a few protons and neutrons to the atomic nucleus. The supernova's shock wave provides the final kick needed to smash these nuclei together, creating heavier elements such as gold, uranium, and the rare earths that power our modern technology. When the blast expands, it carries this enriched material outward, seeding the surrounding gas clouds. Over millions of years, those clouds collapse under their own gravity, forming new stars and planetary systems. In this way, the iron in our blood and the calcium in our bones were forged in the heart of a star that exploded long before the sun was born. The shock wave itself is a force of nature that reshapes its environment. As it barrels through the interstellar medium, it compresses gas, triggers turbulence, and can ignite new pockets of star formation. Imagine a supersonic jet breaking the calm air over a runway. The jet's wake creates ripples that can lift dust and debris. A supernova's shock wave works on a vastly larger scale, sweeping up material at speeds of tens of thousands of kilometers per second, far faster than any aircraft we have built. When the wave slows, it leaves behind a dense shell of gas, a fertile breeding ground for the next generation of stars. Our ability to study these distant cataclysms rests on the fact that they shine across the entire electromagnetic spectrum. In visible light, the expanding nebula glows with vivid reds and blues, each hue telling us about the temperature and composition of the gas. Radio telescopes pick up the faint whispers of electrons spiraling in magnetic fields, revealing the structure of the shock front long after the visible light has faded. Infrared detectors sense the warm dust that forms as the gas cools, while X-ray observatories capture the high-energy photons emitted by the hot interior and by the compact remnants left behind. The most energetic explosions even produce gamma rays, the universe's most penetrating radiation, which can travel across billions of light years to reach our instruments. By stitching together data from all these windows, astronomers build a complete picture of the supernova's life cycle, from the moment of core collapse or detonation to the slow fade of its remnant. Yet many mysteries linger, as if the universe has deliberately left some verses of its story unwritten. For core collapse supernovae, we still debate exactly how the stalled shock wave is revived to explode the star. Some theories invoke intense streams of neutrinos, ghostly particles that barely interact with matter, to re-energize the blast. Others suggest that turbulent motions inside the star play a crucial role. In the realm of Type Ia supernovae, the precise nature of the companion star remains uncertain. Is it a normal star shedding material, or another white dwarf merging in a quiet dance? Each answer reshapes our understanding of how elements are distributed and how we calibrate the cosmic distance ladder. When we look up at a night sky dotted with the faint smudges of ancient remnants, we are witnessing the aftermath of collisions that occurred long before Earth formed. The iron in our planet's core, the silicon in our computers, the oxygen we breathe, all were forged in these stellar furnaces and scattered by the force of a dying star. In that sense, every supernova is both an ending and a beginning, a reminder that destruction and creation are woven together in the tapestry of the cosmos. As the shock wave finally dissipates and the nebula blends into the surrounding clouds, the cycle continues. New stars ignite, planets coalesce, and somewhere, perhaps, life begins to wonder about the fireworks that lit the sky billions of years ago. The story of supernovae is therefore not just a tale of distant explosions, but a chronicle of our own origins, written in starlight and carried across the void. In the next chapter, we will follow that starlight further, tracing how the enriched material travels through the galaxy, eventually joining the swirling arms that cradle new suns and perhaps new minds eager to listen. Imagine two islands of stars, each a galaxy, drifting silently through the darkness until the pull of gravity draws them together like two slow-moving dancers. In the vast emptiness, their meeting is not a sudden crash but a graceful, inevitable intertwining that reshapes everything caught in its grip. This is the story of galactic collisions, where tidal forces stretch and pull, where clouds of gas ignite in brilliant bursts, and where the very shape of a galaxy can be rewritten in a cosmic heartbeat. When two massive galaxies approach, the invisible hand of gravity reaches far beyond the visible stars. It tugs at the outer edges, pulling streams of stars and gas into elongated ribbons that can stretch for hundreds of thousands of light years. These features are known as tidal tails, thin arms that flare outward like the wake of a ship moving through water. Between the galaxies, bridges of material may form, linking the two systems in a luminous filament. To picture a tidal tail, think of a long, thin plume of smoke drifting from a campfire, except each strand contains billions of suns and the dust of countless planets. The stretching does more than create beautiful shapes. It compresses clouds of hydrogen gas, the raw material for new stars. As the galaxies interpenetrate, the gas is shocked, heated, and then forced together in dense knots. In these knots, gravity wins and new stars are born at a furious rate. This phenomenon is called a starburst, a period when a galaxy can form stars 100 times faster than it does in quieter times. If a single star were a candle, a starburst would be a city of lanterns flaring to life all at once, their combined glow outshining the ordinary night. Such bursts are not fleeting fireworks. They can last tens of millions of years, a blink in the life of a galaxy but a long, radiant chapter for the stars within. The newborn massive stars live fast and die young, exploding as supernovae that seed the surrounding space with heavy elements: iron, carbon, oxygen, ingredients essential for planets and ultimately life. In this way, the violent encounter of two galaxies sows the seeds for future generations of worlds, even as it tears apart the old ones. Beyond the fireworks, the very structure of the colliding galaxies begins to change. Spirals, with their graceful arms winding around a bright core, are particularly vulnerable. Their orderly rotation is disrupted as the tidal forces scramble the orbits of stars. Over time, the ordered disk can dissolve, and the stars settle into a more random, spheroidal distribution. The result is often an elliptical galaxy, a smooth, featureless ball of stars that glows uniformly. It is as if the delicate lace of a spiral dress is smoothed into a simple, rounded cloak. The transformation from spiral to elliptical is not instantaneous. It unfolds over hundreds of millions of years, a slow metamorphosis that can be traced in the fossil record of stellar populations. Astronomers can read the ages of stars, the motions of gas, and the shapes of tidal remnants to piece together the timeline of a merger. In many ways, a galaxy merger is a natural laboratory, showing how gravity, gas dynamics, and the life cycles of stars intertwine on a scale that dwarfs human imagination. One of the most vivid examples of this process is the antennae galaxies, a pair of colliding spirals located about 45 million light-years away in the constellation Corvus. Their name comes from the long, curved tidal tails that resemble the antennae of an insect, stretching outward like the arms of a cosmic octopus. In the heart of the collision, bright knots of star formation blaze, visible even in modest telescopes. The antennae offer a front-row seat to a merger in progress, showing both the chaos of tidal disruption and the brilliance of starburst activity. Observations across the spectrum, from radio waves that map cold gas to X-rays that reveal hot supernova remnants, paint a picture of a galaxy pair caught in the act of rebuilding itself. To understand how such intricate structures arise, astronomers turn to computer simulations. By modeling the gravitational pull of billions of particles representing stars, gas, and dark matter, they can replay the dance of two galaxies in a virtual universe. These simulations reveal that the length and curvature of tidal tails depend on the mass ratio of the colliding galaxies, the angle of impact, and the distribution of dark matter halos that envelop them. They also show how gas can lose angular momentum, funneling toward the center and fueling both starbursts and the growth of supermassive black holes. In recent years, simulations have become detailed enough to reproduce the antennae's twin antennae, confirming that our theoretical picture matches the observed reality. Yet, even the most sophisticated models leave questions unanswered. Dark matter, the invisible scaffold that holds galaxies together, influences the merger but cannot be seen directly. Does the distribution of dark matter change dramatically during a collision, or does it remain a silent partner, guiding the stars without being altered? How often do mergers trigger the rapid feeding of central black holes, igniting active galactic nuclei that outshine entire galaxies? And what fraction of the massive elliptical galaxies we see today are the quiet remnants of such tumultuous unions? The answers lie not only in simulations, but also in the faint whispers of ancient light. By looking at distant galaxies whose light has traveled billions of years, astronomers catch glimpses of mergers in their early stages, when the universe was younger and collisions more common. Each observation adds a piece to the puzzle, helping us understand how the grand tapestry of the cosmos has been woven over eons. As we contemplate these colossal encounters, a sense of humility settles in. The forces that reshape galaxies operate over distances measured in light years, far beyond the span of a single solar system, and over timescales that dwarf a human lifetime. Yet the same gravity that pulls galaxies together also holds our own planet in orbit. The same elements forged in the heart of starbursts become part of the air we breathe. In the grand ballet of the universe, every collision, every tidal tail, every burst of newborn stars is a reminder that change is the only constant, and that even the most violent events can give rise to new beauty. In the quiet after the clash, when the tidal tails fade and the stars settle into a new shape, the galaxy carries the memory of its past. It becomes a living archive of cosmic history, its light a story waiting to be read. As we turn our gaze to the next chapter of the universe's dark secrets, we will follow that light deeper into the shadows, seeking the hidden forces that still shape the heavens. In the silent depths of space, titanic clusters of galaxies collide, releasing energies that dwarf the power of 1,000 suns and reshaping the very scaffolding of the cosmos. It is a drama played out over millions of light years, a slow but violent ballet that offers a rare glimpse into the hidden substance that binds the universe together. Imagine a city of galaxies, each a swirling island of stars, gas, and dark matter, gathered in a gravitational embrace that spans several million parsecs. A parsec, a distance of about 3.5 light-years, is already beyond ordinary human experience. A megaparsec stretches that scale 1,000-fold. When two such colossal cities meet, the encounter is not a gentle handshake. It is a cataclysm that tears apart the hot plasma that fills the space between galaxies, while the invisible dark matter passes through almost unscathed. The aftermath is a striking separation, a cosmic fingerprint that tells a story of forces we can only infer. The most celebrated example of this phenomenon is the Bullet Cluster, a pair of galaxy clusters caught in the act of merging. In visible light, the scene appears as a dense collection of galaxies moving together, but the true drama unfolds in X-ray wavelengths. The intracluster plasma, gas heated to tens of millions of degrees, glows fiercely in X-rays, much like the ember of a coal fire, yet spread across a region larger than the Milky Way. When the two clusters collided, this plasma behaved like a thick, viscous fluid. It slammed into the opposing cloud, slowed, and was forced to pile up, forming a bright, bow-shaped shock front that stretches across hundreds of thousands of light years. Meanwhile, the dark matter, which makes up roughly 85% of the total mass of the clusters, does not interact with the plasma. It simply streams through, guided only by gravity. Astronomers map its distribution by measuring how the clusters bend the light from more distant galaxies, a phenomenon known as gravitational lensing. The resulting lensing map shows two massive clumps of dark matter that sit ahead of the bright X-ray glow. This offset between the luminous gas and the unseen mass is the hallmark of a collision on megaparsec scales. The significance of that offset extends far beyond a striking visual. It provides a natural laboratory for testing the very nature of dark matter. If dark matter were composed of particles that interact strongly with ordinary matter, the collision would have produced a different pattern, with the dark components slowed and dragged along with the plasma. The observed separation suggests that dark matter interacts only through gravity, reinforcing the prevailing view that it is essentially collisionless. Yet the precision of the measurement leaves room for subtle forces, perhaps a whisper of self-interaction that could reshape our theories. The bullet cluster thus stands as a cosmic experiment that we cannot replicate on Earth, yet it yields clues about the invisible scaffolding of the universe. Beyond the immediate drama, the collision reverberates through the larger cosmic web. Galaxy clusters are the knots in a vast network of filaments and voids, the grandest structures formed from the slow growth of tiny density fluctuations after the Big Bang. When two clusters merge, they inject turbulence into the surrounding intergalactic medium, stir magnetic fields, and accelerate particles to near light speeds. These energetic particles, known as cosmic rays, can travel across the web, seeding distant regions with high-energy particles that influence the formation of new galaxies. The shock waves generated by the impact can also compress gas in neighboring filaments, potentially triggering bursts of star formation far from the original collision site. In this way, a single megaparsec scale event can echo across the tapestry of the cosmos, shaping the evolution of structures billions of light-years away. Observing these distant, violent encounters requires instruments that can capture the faint X-ray glow of hot plasma against the darkness of space. Current observatories, such as the Chandra X-ray Observatory, have provided the sharp images that reveal the shock fronts and the displaced gas in the bullet cluster. Yet their sensitivity limits the number of collisions we can study in detail. Future missions promise to widen our view. The upcoming Athena, Advanced Telescope for High-Energy Astrophysics, will combine unprecedented collecting area with high-resolution spectroscopy, allowing astronomers to map the temperature, velocity, and chemical composition of the intracluster medium with exquisite precision. With such data, we will be able to trace the flow of gas in 3 dimensions, watching how it slows, mixes, and cools after a collision. Another planned mission, Lynx, aims to push the detection of faint X-ray sources even farther, potentially uncovering a hidden population of merging clusters at earlier epochs of the universe. These instruments will turn the study of cluster catastrophes from a handful of case studies into a statistical science, revealing how common such collisions are and how they influence the growth of the cosmic web over time. The story of these colossal crashes also invites deeper philosophical reflection. In the vastness of the universe, the forces that govern the motion of galaxies are indifferent to human concerns, yet they shape the very environment in which we exist. The same dark matter that guides the dance of clusters also cradles our own Milky Way, anchoring it within the larger filamentary network. The hot plasma that glows in X-rays is a reminder that even the emptiest regions of space are filled with energetic particles and magnetic fields, a dynamic medium that has been alive for billions of years. When clusters collide, they remind us that the cosmos is not a static backdrop, but a living, evolving entity, where creation and destruction are intertwined. As we listen to the faint whispers of X-ray photons traveling across the gulf of time, we are reminded that each photon carries a story of a moment when matter was torn apart and reassembled. The bullet cluster and its kin are not merely spectacular pictures. They are chapters in the ongoing saga of the universe, chapters that reveal how the unseen and the visible interact, how gravity sculpts structure, and how energy is redistributed on the grandest scales. By studying these megaparsec-scale collisions, we edge closer to answering one of the most profound questions of modern physics. What is the nature of the dark matter that dominates the mass of the cosmos? The next step in our journey will follow the threads of these collisions outward, into the vast filaments that connect clusters like bridges across a cosmic sea. There, the subtle imprint of past crashes lingers, waiting for the next generation of telescopes to uncover. In that exploration, we will see how the remnants of ancient cataclysms continue to influence the birth of galaxies, the formation of stars, and perhaps even the conditions that allowed life to arise. The universe, in its quiet grandeur, holds its secrets close, but with each observation we draw a little nearer to the heart of its mystery. When two black holes collide, the universe trembles. Its very fabric ripples outward like a stone dropped in a pond of spacetime. In that fleeting instant, a burst of energy far greater than all the stars in a galaxy is released, not as light, but as a wave that carries the memory of the encounter across billions of light years. It is a whisper from the most violent dance in the cosmos, and it is this whisper that we now hear. The story begins with a pair of massive stars, each many times the mass of our Sun, locked together in a binary orbit. Over millions of years they burn their nuclear fuel, shining bright before they exhaust their core. When the fuel runs out, each star collapses under its own gravity, leaving behind a black hole, a region where gravity is so strong that not even light can escape. The two remnants continue their orbit, spiraling ever closer as they lose energy. This loss is not through ordinary radiation, but through the emission of gravitational waves, ripples that travel outward at the speed of light, stretching and squeezing space itself. Imagine two ice skaters holding hands on a frozen lake, spinning slowly at first, then drawing their arms inward. As they pull together, they spin faster, and the sound of their blades on the ice grows louder. In the cosmic version, the sound is a wave in spacetime, and the ice is the very arena of the universe. The closer the black holes come, the more powerful the wave, until finally they merge into a single, more massive black hole. The moment of merger is a crescendo, a burst of gravitational energy that carries away a few percent of the combined mass, transformed into pure curvature of space. It was only in 2015 that humanity first caught this cosmic crescendo. The twin detectors of the Laser Interferometer Gravitational Wave Observatory, perched in the quiet valleys of Washington and Louisiana, sensed a fleeting distortion in their laser beams. For a fraction of a second, the length of each arm changed by less than the width of a proton. Yet that minute shift revealed a cataclysmic event. Two black holes, each about 30 times the mass of the Sun, spiraling together and merging over 1 billion light-years away. The signal, named GW150914, was the first direct proof that gravitational waves exist, confirming a prediction made by Einstein a century earlier. Each detection since then has added a new note to the symphony of the universe. The Virgo detector in Italy, joining LIGO's network, has helped pinpoint where the waves originated, allowing astronomers to look toward the same region of sky with telescopes. Though black holes swallow light, the surrounding environment can glow when gas is torn apart and heated before the final plunge. In a few rare cases, a faint flash of light has been seen minutes after a gravitational wave alert, hinting at a possible connection between black hole mergers and the surrounding matter. These observations weave together the invisible and the visible, giving us a fuller picture of how such collisions shape the cosmos. One of the most profound questions that arises from these events is how the most massive black holes, those that sit at the centers of galaxies, came to be. Supermassive black holes can weigh millions or even billions of times the Sun, yet the universe is only 13.8 billion years old. How could such giants grow so quickly? One compelling pathway is through a series of binary mergers. When galaxies collide, their central black holes are drawn together, forming a binary that eventually coalesces, adding their masses. Over cosmic time, repeated mergers can build a leviathan from smaller seeds. Much like a snowball rolling down a hill gathers more snow with each turn. Gravitational wave observations of stellar mass black holes provide a window into this process, showing that mergers are not rare, but a natural part of black hole evolution. The physics at the edge of a black hole, the event horizon, remains a realm of mystery. The horizon is the point of no return where the escape velocity equals the speed of light. Yet, according to quantum theory, the horizon is not a perfectly smooth surface. Tiny fluctuations may give rise to a faint glow, known as Hawking radiation, that slowly erodes the black hole over unimaginable timescales. The merger of two horizons creates a new, larger horizon that settles down through a process called ringdown, emitting gravitational waves that decay like the fading tone of a struck bell. By listening to this ringdown, scientists can test whether the newly formed object behaves exactly as Einstein's theory predicts, or whether subtle deviations hint at new physics. The detectors that have opened this new sense are marvels of engineering, yet they are limited by the Earth's own restless nature. Seismic tremors, passing trucks, even the subtle sway of the ground beneath the instruments can mask the faint signals from distant mergers. To push beyond these limits, the next generation of observatories will take to space. A constellation of 3 spacecraft, forming a giant laser interferometer millions of kilometers long, will orbit the Sun in a configuration that isolates it from terrestrial noise. This space-based detector, known as LISA, will be sensitive to lower-frequency gravitational waves, those produced by massive black holes merging in the early universe, and by compact objects spiraling into supermassive black holes. With LISA, we will be able to hear the deep bass notes of the cosmos, hearing events that are invisible to ground-based observatories. The promise of space-based detection is not only to increase the number of observed events, but also to open new windows on the universe's history. The first black holes likely formed from the collapse of the very first massive stars, some a few hundred million years after the Big Bang. Their mergers would have generated low-frequency waves that have traveled across the expanding universe, stretched by cosmic expansion, and now arrive at us as gentle ripples. By decoding these ancient signals, we can learn about the conditions of the early cosmos, the formation of the first galaxies, and the seeds of the supermassive black holes that dominate today's galactic centers. Even as we listen, we are reminded of the profound humility of our place in the universe. The forces that drive black hole collisions are far beyond anything we can imagine on Earth. Yet, through clever instruments and patient observation, we have become attuned to a language that the universe has spoken since its first moments. Each detection is a reminder that the cosmos is not silent. It is alive with vibrations that carry stories of creation, destruction, and renewal. As the final notes of a merger fade, the newly formed black hole settles into a quiet existence, its horizon a calm sea after a storm of spacetime. Yet the waves it emitted continue to travel, crossing galaxies, bending the paths of light, and eventually reaching our detectors. In that journey lies a bridge between the immeasurable scales of the universe and the human desire to understand. The afterglow of a collision is not only a scientific triumph, It is a testament to curiosity, to the willingness to listen to the faintest of whispers. The next chapter will turn our attention to the shadows cast by these titanic events, exploring how the remnants of collisions shape the galaxies that host them, and how the very act of merging can seed the birth of new stars. In the quiet after the storm, the universe prepares for its next act, and we stand ready to hear it. When we look up at the night sky, we see a calm sea of stars, but hidden within that quiet light are the scars of ancient collisions that shaped our galaxy. Those scars are not obvious to the eye. They are faint rivers of stars, ghostly trails that whisper of dwarf galaxies torn apart long ago. In the quiet of the Milky Way's halo, these stellar streams form a fossil record, a cosmic archaeology that lets us read the story of our galaxy's growth. The Milky Way is not a solitary island. Over billions of years it has swallowed smaller companions, much as a river gathers tributaries. Each time a dwarf galaxy drifts too close, the immense gravity of the Milky Way stretches it, pulling its stars into elongated ribbons that wrap around the galactic center. These ribbons, stellar streams, are the remnants of those encounters. They are thin, faint, and stretch across the sky like the delicate threads of a tapestry, each one a reminder that the galaxy we call home is a patchwork of many past lives. Detecting these streams is a delicate art. The stars that belong to a stream move together, sharing a common speed and direction, yet they are intermingled with countless other stars that belong to the smooth background of the halo. For decades, astronomers could only glimpse the brightest streams, such as the one left by the Sagittarius dwarf galaxy, a small companion that is currently being shredded. The Sagittarius stream arcs across the sky in two long, graceful arms, looping above and below the galactic plane. Its discovery revealed that the Milky Way is still actively accreting material, and it gave the first clear picture of a dwarf galaxy in the act of disintegration. The breakthrough came with the launch of the Gaia spacecraft. By measuring the positions, distances, and motions of more than 1 billion stars with unprecedented precision, Gaia turned the night sky into a three-dimensional map. In that map, the halo of the Milky Way began to resolve into a complex network of substructures. Tiny clumps of stars that share similar velocities stand out against the random motions of the surrounding population. These substructures are the fingerprints of past mergers, each one a lingering echo of a galaxy that fell into the Milky Way's grasp. One of the most striking findings from Gaia is the discovery of multiple, overlapping streams that criss-cross the halo. Some of these streams are ancient, their stars having completed many orbits around the galactic center, while others are relatively young, still retaining the shape of their progenitor. By tracing the paths of these streams backward, astronomers can infer the original orbits of the dwarf galaxies that birthed them, and thus reconstruct the timeline of the Milky Way's assembly. But motion alone does not tell the whole story. The stars that belong to a given stream also share a chemical heritage. Elements such as iron, magnesium, and calcium are forged in the hearts of stars and released when those stars die. The particular mix of these elements, often called a star's chemical fingerprint, records the environment in which the star formed. When a dwarf galaxy is torn apart, its stars carry this unique chemical signature into the Milky Way's halo. By measuring the abundances of many elements in individual stars, a technique known as chemical tagging, astronomers can link stars that were born together, even if they are now scattered across the sky. Chemical tagging has revealed that many of the halo's stars do not belong to the Milky Way's original population. Instead, they bear the low metallicity patterns typical of small, ancient dwarf galaxies. Some streams, like the one from the Gaia Sausage Enceladus event, show a distinct chemical composition that differs from the Sagittarius stream, indicating that they originated from separate progenitors. The ability to match chemistry with motion provides a powerful double check, confirming that a group of stars truly shares a common ancestry. The implications of this growing fossil record are profound. First, they show that the Milky Way's mass has been built up piece by piece, rather than forming in a single monolithic collapse. The galaxy's thick disk, its halo, and even parts of its thin disk bear the imprint of past mergers. Each accreted dwarf galaxy contributed not only stars, but also dark matter, gas, and angular momentum, reshaping the Milky Way's structure over time. The Sagittarius dwarf, for example, is currently depositing fresh gas that may fuel future star formation, while its gravitational tug has stirred the Milky Way's disk, possibly creating ripples that we can observe today. Second, the timing of these events offers clues about the broader history of the universe. By estimating the ages of stars in a stream, using their brightness, temperature, and chemical composition, astronomers can date when the merger occurred. Some streams trace back to a time when the universe was less than a quarter of its current age, a period when galaxies were still rapidly assembling. Others are more recent, showing that the Milky Way's growth has continued up to the present day. This continuous accretion challenges earlier models that imagined a relatively quiet recent past for our galaxy. Third, the study of stellar streams informs our understanding of dark matter. The shape and width of a stream are sensitive to the gravitational field it moves through. If the Milky Way's dark matter halo were perfectly smooth, a stream would remain narrow and coherent. However, the presence of clumps, small dark matter subhalos predicted by cosmological theory, can disturb a stream, creating gaps and wiggles. By mapping these perturbations, scientists can test the nature of dark matter itself, probing whether it is cold, warm, or something more exotic. While the picture that emerges is increasingly detailed, many questions remain. How many dwarf galaxies have been completely dissolved, leaving only faint streams that we have yet to detect? What role did the Milky Way's own bar and spiral arms play in shaping the orbits of accreted material? How does the influx of gas from mergers influence the chemical evolution of the disk over billions of years? Future data releases from Gaia, combined with spectroscopic surveys that measure stellar chemistry on a massive scale, promise to answer some of these mysteries. In the stillness of the night, the Milky Way's halo glows faintly, a silent witness to countless encounters. The streams that thread through it are like the rings of a tree, each one marking a season of growth, a collision, a transformation. As we follow these stellar rivers back to their sources, we learn that our galaxy is not a static island but a living, evolving structure, constantly reshaped by the pull of gravity and the flow of time. The story of these ancient impacts invites us to contemplate our place within a universe that is ever-changing. The stars that shine above us are not isolated points of light. They are the remnants of distant worlds that once roamed their own realms before becoming part of a larger whole. In tracing their journeys, we not only map the Milky Way's past, but also glimpse the processes that will shape its future. The next chapter will turn our gaze outward, to the vast cosmic web that connects galaxies across the expanse, and to the hidden forces that bind the universe together. In the darkness that stretched beyond the first flicker of light, the universe was a restless sea of gas and shadow, waiting for the moment when the first sparks could turn night into day. It was in those first few 100 million years that the cosmos began to collide, to merge, and to awaken, setting the stage for everything that would ever follow. When the Big Bang unfolded, it left behind a hot, dense broth of hydrogen, helium, and a trace of lithium. This primordial soup expanded, cooled, and eventually formed the first clouds of gas, each the size of a small galaxy, yet far more diffuse than the wispy clouds we see in our own sky. Within these clouds, gravity, though gentle, started to pull matter together, coaxing the gas into denser knots. In those knots, the first stars were born, unlike any that shine today. These first luminous beings are called population III stars. They were forged from pure hydrogen and helium, untouched by the heavy elements that later generations would inherit. Because they contained no metals to help cool the gas, they grew massive, often hundreds of times the mass of our Sun. Imagine a star so large that if it were placed where the Sun now sits, it would swallow the orbit of Mercury and still shine with a brilliance that could outshine 1,000 suns. Such giants lived fast and died young, exploding as supernovae after only a few million years. Their deaths scattered the first heavy elements, carbon, oxygen, iron, into the surrounding medium, seeding the universe with the ingredients needed for planets and, eventually, life. But stars did not form in isolation. The early universe was a crowded place, with countless nascent galaxies drifting close to one another. Their motions, guided by the invisible scaffolding of dark matter, brought them together in a cosmic dance of collisions. In the first billion years, the rate of these mergers was far higher than what we observe in the mature universe today. Where a typical galaxy today might wait billions of years before encountering a comparable partner, a young galaxy in the early epoch could be swept up in a merger within a few 100 million years, a blink in cosmic time. Each collision was more than a simple merging of stars. It was a catalyst that reshaped the very fabric of the surrounding space. When two proto-galaxies collided, their gas clouds compressed, igniting bursts of star formation. The turbulence stirred the interstellar medium, feeding the growth of new population III stars, and soon after, their metal-rich descendants. These starbursts released torrents of energetic photons, particles of light so powerful they could strip electrons from the neutral hydrogen that filled the universe. This process, known as reionization, turned the opaque fog of the early cosmos into a transparent sea of ionized gas, allowing light to travel freely across vast distances. Reionization did not happen all at once. It unfolded over several 100 million years, beginning perhaps as early as 300 million years after the Big Bang, and completing around 1 billion years later. Early galaxies, especially those undergoing frequent mergers, acted as lanterns in the darkness, each contributing to the gradual brightening of the universe. As more galaxies merged, the combined star formation rates rose, accelerating the ionizing photon budget. Yet, despite the progress we have made in mapping this era, many questions remain. How much of the ionizing radiation escaped the dense gas of young galaxies? Which types of galaxies, small, faint dwarfs, or larger, more luminous systems, were the primary drivers? The answers lie hidden in the faint whispers of the distant past. For decades, these whispers were beyond our reach. The light from the earliest galaxies has traveled for billions of years, stretched by the expansion of space into infrared wavelengths that our most sensitive instruments could not detect. The launch of the James Webb Space Telescope changed that picture dramatically. With its powerful infrared eyes, JWST has begun to capture the faint glow of galaxies that formed when the universe was less than 1/10 of its current age. In some of its deepest fields, the telescope has revealed pairs of galaxies caught in the act of merging, their distorted shapes and tidal bridges, a testament to the violent interactions that were common in those early times. One remarkable observation shows two compact galaxies, each no larger than a few thousand light-years across, locked together in a graceful spiral of gas and stars. Their combined brightness suggests a star formation rate far exceeding that of typical galaxies at the same epoch. Spectra taken by JWST indicate the presence of ionized oxygen and neon, elements that could only have been forged in previous generations of stars, signaling that even at such an early stage, the universe had already begun to recycle its material. These high redshift mergers provide a direct window into the mechanisms that powered reionization, confirming that collisions were not merely incidental but central to the process. Theoretical models have long predicted that the early universe would be a hotbed of mergers, driven by the hierarchical nature of structure formation. In these models, tiny fluctuations in the density of the primordial gas, imprinted in the cosmic microwave background, served as seeds for dark matter halos. Over time, smaller halos merged to form larger ones, pulling the gas within them into deeper potential wells. Simulations that track billions of particles show a cascade of mergers, where each generation builds upon the last, creating the web-like structure we observe today. These simulations also reveal that the merger rate peaks when the universe is only a few 100 million years old, then gradually declines as the expansion stretches galaxies farther apart. Yet, models must be tested against observation. The JWST data have already forced refinements to our understanding. For instance, the observed frequency of massive, metal-rich galaxies at redshifts greater than 10 suggests that star formation and chemical enrichment proceeded more rapidly than some simulations had allowed. This discrepancy prompts researchers to explore alternative pathways, perhaps more efficient cooling mechanisms, or the influence of exotic processes such as dark matter annihilation, that could accelerate the birth of stars and the buildup of heavy elements. Beyond the technical details, there is a profound sense of connection in these early collisions. The same forces that drove tiny clouds of hydrogen to coalesce, ignite, and explode also set in motion the chain of events that would eventually give rise to planets, oceans, and consciousness. The atoms forged in the hearts of population III supernovae have traveled across billions of light years, become part of later generations of stars, and now reside in the very breath we take. The universe's earliest fireworks were not isolated spectacles. They were the first verses in a cosmic poem that continues to unfold. As we listen to the faint echoes of these ancient mergers, we are reminded of the delicate balance between chaos and order that has shaped the cosmos. The violent encounters that once tore galaxies apart also forged the conditions for stability, allowing gas to settle, stars to form, and galaxies to mature into the graceful spirals and massive ellipticals we see today. In the quiet moments between collisions, the universe took time to breathe, to let the newly created elements mix, and to prepare for the next act in its long story. Looking ahead, the next generation of telescopes will push even deeper into this primordial epoch. Instruments that can capture the faint glow of the first dwarf galaxies, or map the distribution of neutral hydrogen with unprecedented precision, will help answer lingering mysteries. Will we find that reionization was driven by countless tiny galaxies, each contributing a modest amount of light, or by a few spectacularly bright mergers? How did the first black holes, born from the collapse of massive population III stars, influence the surrounding gas and the pace of reionization? These questions linger like shadows at the edge of a sunrise, waiting for the light of discovery to reveal them. In the grand tapestry of the universe, the early collisions were the first threads woven together, binding gas, dust, and darkness into patterns that would endure for eons. They remind us that the cosmos is not a static backdrop, but a living, evolving entity, one that has been shaped by countless moments of contact, compression, and creation. As we turn our gaze toward the next chapter of this story, we carry with us the wonder that those first violent embraces set the rhythm for everything that followed, echoing across time and space in a melody that still resonates within us. In the darkness between the stars, a hidden dance unfolds, one that we cannot see, cannot touch, yet shapes the very scaffolding of the cosmos. For centuries, we have mapped the bright tapestry of galaxies, traced the glow of nebulae, and measured the pull of gravity with the precision of a clockmaker. Yet an unseen majority, dark matter, continues to whisper its secrets, inviting us to imagine collisions that leave no flash of light, to hear the faint echo of particles that barely brush one another, and to question whether the force that holds the universe together might be something altogether different. Imagine a vast, invisible ocean filling the space between galaxies, its currents invisible to any telescope. In the ordinary world, water molecules glide past each other, rarely colliding in a way that changes their motion. For a long time, scientists thought dark matter behaved much the same, particles that passed through each other and through ordinary matter without a single sigh. This picture, called cold dark matter, has guided simulations that reproduce the grand web of galaxy clusters we observe. Yet when we peer more closely, the universe begins to reveal cracks in that simple story. One of those cracks appears in the form of the missing satellite problem. Our own Milky Way, a sprawling spiral of 100 billion stars, should be surrounded by thousands of tiny dwarf galaxies, the remnants of small clumps of dark matter that never grew large enough to ignite bright stars. Computer models based on non-interacting dark matter predict a bustling swarm of these diminutive companions, like a sky full of fireflies. When we look up with our most sensitive instruments, we find only a few dozen. The night sky is quieter than the models demand. Why do so many expected satellites vanish? One compelling possibility is that dark matter is not entirely aloof. In self-interacting dark matter scenarios, the particles that make up the invisible halo can collide with one another, exchanging momentum much as billiard balls do on a pool table. These collisions would soften the dense cores of dark matter halos, allowing the smallest clumps to be torn apart more easily by the gravitational tides of larger galaxies. In this view, the missing satellites are not absent because they never formed, but because they have been shredded by a gentle, pervasive friction that only dark matter feels. The notion of particles that interact with themselves invites us to imagine a cosmic fog, thick enough to slow the motion of its own droplets, yet thin enough to let light pass unhindered. If such a fog exists, its fingerprints would be subtle. In the hearts of galaxy clusters, we would see dark matter cores that are rounder and less dense than predicted by a collision-free model. In dwarf galaxies, the distribution of stars would trace a smoother, more uniform gravitational well. Observations of these systems have indeed hinted at such softness, but the evidence remains tentative, like a faint ripple on a distant pond. While self-interacting dark matter offers one avenue, another line of thought asks whether the force we call gravity might need a new description on galactic scales. Modified Newtonian dynamics, or MOND, proposes that at accelerations far weaker than those we experience on Earth, the familiar law of gravity changes its behavior. In the outskirts of a galaxy, where the pull of the visible stars is feeble, MOND predicts a stronger effective attraction, accounting for the flat rotation curves without invoking unseen mass. This elegant idea reproduces many galactic observations with startling accuracy, yet it struggles to explain the dynamics of massive clusters and the cosmic microwave background, where dark matter still seems indispensable. The tension between these two perspectives, new particle physics versus new gravity, drives a vibrant debate. Each offers a different lens through which to view the same mysteries, and each demands new tests. The coming decade promises a suite of surveys designed to listen for the faintest whispers of dark matter scattering. Deep underground laboratories, shielded from cosmic rays, will host detectors cooled to near absolute zero, ready to capture the minuscule recoil of a dark particle striking an atomic nucleus. Meanwhile, space-borne telescopes will map the distribution of dark matter across billions of light years by measuring the subtle distortion of background galaxies, a technique known as weak gravitational lensing. By comparing regions where dark matter appears more clumped with predictions from self-interacting models, scientists hope to catch a glimpse of the hidden collisions. Another promising avenue lies in the study of galaxy clusters that have recently merged. When two massive clusters collide, their galaxies, hot gas and dark matter, separate in distinct ways. The luminous gas slows down, creating a bright X-ray glow, while the galaxies, largely empty space, pass through relatively unimpeded. If dark matter also interacts, it would lag behind the galaxies, forming a telltale offset that could be measured with precise lensing maps. So far, observations of the famous Bullet cluster have shown dark matter aligning with the galaxies, suggesting that any self-interaction must be weak, no more than a few percent of the chance of particles colliding as they pass through each other. Yet a handful of newer cluster collisions hint at small deviations, keeping the question alive. Even as instruments become more sensitive, the fundamental nature of dark matter remains an open question. Could it be composed of a single, massive particle that rarely interacts, or a family of lighter particles that exchange forces among themselves? Might dark matter form its own complex structures, perhaps even dark stars or dark planets, hidden from our sight but influencing the motions of ordinary matter? Or could the answer lie not in unseen particles at all, but in a deeper understanding of space-time, where the geometry of the universe itself bends differently on vast scales? These mysteries are not merely academic. They touch upon the very origin story of the cosmos, the way galaxies assembled, and the ultimate fate of the universe. If dark matter self-interacts, the growth of cosmic structures could be slower, altering the timeline of galaxy formation. If gravity behaves differently, the expansion of space might accelerate or decelerate in ways we have yet to grasp. Each scenario reshapes the narrative of how the universe evolved from a hot, dense beginning to the intricate web of stars and voids we inhabit today. The pursuit of answers is a patient one, built on layers of observation, theory, and imagination. Researchers are training artificial intelligence to sift through petabytes of survey data, searching for patterns that human eyes might miss. They are constructing ever larger detectors deep beneath mountains, where the Earth itself shields the fragile experiments from background noise. They are launching satellites that will chart the sky with unprecedented resolution, mapping the invisible scaffolding that guides galaxies like invisible hands. Every new piece of data adds a brushstroke to a picture that remains, for now, unfinished. As we listen to the cosmos, we are reminded that darkness is not merely an absence of light, but a realm of possibilities. The hidden collisions of dark matter may never produce a flash, yet they may leave an imprint in the way galaxies spin, in the shape of dwarf satellites, in the subtle shift of light from distant quasars. The unanswered questions stand as invitations, prompts for the next generation of explorers to devise experiments, to craft new theories, to peer deeper into the night. In the quiet moments between the hum of detectors and the glow of computer screens, there is a sense of humility. We are trying to understand a substance that does not shine, does not absorb, does not emit, yet outweighs everything we can see by a factor of 5. It reminds us that the universe holds more than our eyes can capture, that the story of existence is still being written in the shadows. The next chapter of this story will emerge not from a single revelation, but from the collective effort of countless minds turning their curiosity toward the unseen. And so, as the night sky stretches above us, speckled with the familiar constellations, we are called to look beyond the stars, to contemplate the invisible threads that bind them. In the darkness, there are collisions, whispers, and possibilities waiting to be uncovered, each a step toward unveiling the ancient secrets that shape our universe. Imagine a map that shows not only the shining stars, but also the invisible collisions that have stitched the universe together. a chart of shadows and ripples that tell the story of every galaxy's birth and every black hole's dance. In the quiet of a night sky, that map has remained hidden, but a new generation of eyes and minds is poised to bring it into view. The European Space Agency's Euclid mission is the first step toward that grand cartography. Launched to orbit far from Earth's bustling atmosphere, Euclid peers across billions of light years, measuring the subtle stretch of space caused by gravity. It does not look for light alone. It watches how galaxies appear slightly distorted, as if seen through a gentle lens of unseen mass. By recording millions of such distortions, Euclid sketches the scaffolding of dark matter, the invisible backbone upon which ordinary matter clings. The patterns it uncovers are the fingerprints of ancient collisions, galaxies that have merged, clusters that have slammed together, and the silent tides that have reshaped entire regions of the cosmos. While Euclid draws the outline, the Nancy Grace Roman Space Telescope, NASA's forthcoming observatory, adds depth with its wide-field infrared eye. Infrared light can slip through dust and travel across the cold reaches of space, revealing galaxies that formed when the universe was only a few 100 million years old. Roman will capture the faint glow of these early structures, allowing scientists to trace how the first massive collisions set the stage for the grand architecture we see today. Together, Euclid and Roman act like two hands, one tracing the invisible scaffolding, the other illuminating the luminous bricks that fill it. Yet gravity's whispers are not limited to light. When massive objects collide, two neutron stars spiraling into each other, or black holes merging, their union sends ripples through spacetime itself. These gravitational waves travel at the speed of light, stretching and squeezing the very fabric of the universe. The detectors that first heard these waves, such as LIGO and Virgo, opened a new sense for astronomy, but they listen only to the most violent nearby events. The next generation of detectors, Einstein Telescope in Europe and Cosmic Explorer in the United States, will be far more sensitive, listening to the faint murmur of collisions that occurred when the universe was still in its infancy. They will hear the echo of black holes that formed from the first generation of stars, and perhaps the subtle tremor of dark matter clumps merging in the distant past. By mapping where these waves arrive from, astronomers will add a three-dimensional layer to the invisible map, pinpointing collisions that left no light behind. Even beyond the reach of light and gravity, a quiet signal fills the cosmos, a faint glow at a wavelength of 21 centimeters, emitted by neutral hydrogen atoms. After the universe's first stars ignited, the hydrogen gas was gradually heated and ionized, but a long, dark age persisted, when the cosmos was a cold, opaque sea. By listening to the 21-centimeter line, scientists can reconstruct a three-dimensional picture of that era, seeing where pockets of matter gathered and where they were torn apart. New radio arrays, such as the hydrogen epoch of reionization array and the planned square-kilometer array, are designed to capture this delicate whisper. They will turn the dark age into a detailed atlas, showing the rise of the first structures and the collisions that sparked the first bursts of starlight. All of these instruments will generate torrents of data, petabytes of images, waveforms, and spectra. To turn this flood into a coherent map, astronomers are turning to machine learning, a form of artificial intelligence that can recognize patterns far beyond human capacity. Neural networks are already being trained to identify the subtle distortions in Euclid's galaxy shapes, to separate true gravitational lenses from instrumental artifacts. In the realm of gravitational waves, deep learning algorithms sift through noisy detector streams, flagging potential signals in fractions of a second. For 21-centimeter cosmology, machine learning models learn to distinguish the faint cosmic signal from foreground interference caused by our own galaxy. These tools act as tireless assistants, constantly refining the map as new observations arrive. The vision that emerges from these combined efforts is a fully mapped dark universe, a tapestry where every filament of dark matter, every ancient merger, and every hidden wave is plotted with unprecedented precision. Such a map would not only satisfy a profound curiosity about where we come from, it would also provide a laboratory for testing the deepest laws of physics. By comparing the observed distribution of dark matter with predictions from theories of gravity, scientists could confirm, or challenge, our current understanding of the cosmos. The timing and frequency of ancient collisions, recorded in gravitational waves and 21-centimeter maps, could reveal whether dark matter is made of particles we have yet to detect, or whether a different, perhaps more exotic, force shapes the universe. Even as we stand on the cusp of this new era, mysteries linger like shadows at the edge of a lantern's glow. Will the next generation detectors uncover collisions that occurred before the first stars ever shone? Might the 21-centimeter surveys reveal unexpected voids, suggesting that unseen forces sculpted the early universe in ways we have not imagined? And as machine learning grows more sophisticated, will it uncover patterns that point to new physics, or will it simply amplify the limits of our current models? The pursuit of an invisible map reminds us that the universe is not only what we see, but also what we have yet to perceive. Each new observatory, each algorithm, each faint signal is a step toward a deeper communion with the cosmos, a reminder that the story of the stars is also the story of the spaces between them, the collisions that never left a flash, and the forces that silently guide the dance of galaxies. As we finish this chapter of anticipation, the horizon ahead is both familiar and astonishing. The instruments we have described will soon launch, awaken, and begin their quiet work, while the algorithms already humming in data centers wait to translate raw measurements into meaning. Together, they will turn the unseen into the known, and in doing so, they will invite us to reflect on our place within a universe that has been, and continues to be, shaped by forces far older than any human memory. The next step, then, is not merely to observe, but to listen, to the faint hum of hydrogen, to the distant tremor of merging black holes, to the subtle stretch of space itself. In that listening, we will find the hidden cartography of ancient collisions, and with it, a clearer picture of the grand tapestry that stretches from the first spark of creation to the quiet corners of today's night sky. The journey forward is a quiet one, guided by patient eyes and patient minds, and it promises to reveal a cosmos more intricate, more connected, and more wondrous than we have ever imagined.